Hey everybody, welcome to DNews and NASA JPL's monthly Space Out. We get together with stars from NASA's Jet Propulsion Laboratory. We talk space, technology, the future of planetary science, and all sorts of great stuff. I'm Trace, and here with me today is DiscoveryNews.com space producer Ian O'Neill. What's up, Ian?
Thank you, Trace. Yeah, so today we're very lucky to have with us Kevin Hand. He's the JPL astrobiologist and deputy chief scientist of solar system exploration. We got Bobak Ferdowsi, JPL engineer and proposed Europa Clipper mission team. He's also the NASA Mohawk Guy. You may remember him as. We've also got Morgan Cable. She is she's a chemist and she's also a JPL scientist. So I really wanted to hand over to you guys just briefly, just to talk about what you're working on right now, what you love about your work. So I'll hand over to Kevin first.
Excellent. Well, pleasure to be here. A great crowd. And briefly, the big picture goal, the question that's motivated my research since I was 10 years old is this question of whether or not we are alone. Is there life beyond Earth? And from an astrobiology perspective, when we think about potentially habitable environments beyond the Earth, we're looking for liquid water, we're looking for the building blocks of life, and we're looking for energy. And for the most part, everybody appreciates that Mars is a very compelling place to look for life beyond Earth. But much of our exploration of Mars focuses on evidence of life as preserved in the rock record, evidence of life as preserved in the layers of the rocks. I want to find living life. I want to find life that's alive today and see whether or not it represents a second origin, to see whether or not DNA, RNA, and proteins is the only game in town. Is there another way of getting the business of life done? And to do that, we need to explore worlds that have liquid water today and have the energy and elements to help build and power life. And so with those constraints, I would argue that the two most compelling worlds to explore are Jupiter's moon Europa and Saturn's moon Enceladus. And so a lot of what I do on a day-to-day basis is lab work, numerical modeling, instrument and mission design to try and pursue this question of whether or not there is life beyond Earth.
Okay. Thank you very much, Kevin. If we can go over to Bobak, just give us a brief overview of what you're doing.
Sure, I'm an engineer here at JPL. I guess I always like making things happen. I like answering the questions, I guess, that kind of Kevin proposed, but also just how do we do those challenging things? How do we solve those difficult problems? And so ended up here working on the Mars program on Curiosity, and now as a Europa Clipper study mission planning, which my day-to-day involves looking at different trades between flight system elements and ground elements, what we can do with the different designs that we're sort of evaluating, and just seeing what sort of the realm of possibility is, and can we make this mission a reality.
Awesome. And Morgan, what do you do?
So, hey everybody, my name is Morgan. Can you hear me? I unmuted myself. Okay. So I am a chemist and sort of an astrobiologist too, and I'm interested in looking for life in extreme environments. There are plenty of places on Earth where they may seem really extreme. They may be really hot, really cold, very dry, and pretty much every place that we have looked for life on Earth, we found it. And a lot of these places can be very good analogs for places elsewhere in our solar system, like Europa. So I'm interested in studying these forms of life, challenging them, figuring out where the cutoff is of where life can survive, and trying to learn about other places in our solar system where these organisms could potentially live, like Europa.
That's so much fun. It sounds amazing.
Sorry, I was on mute then. Yeah, so really, I wanted to kick off. This is a question for everybody, really, and to be honest, I mean, a lot of our readers, and me personally, I'm fascinated with Europa for the potential that it has. But I kind of wanted to put it out there. What fascinates you most about Europa in particular? I mean, Kevin kind of touched on it with the potential that it has. But what's the specific things that really get you excited? So I suppose we can start with Kevin again and just work through.
Well, so we now know of perhaps 6 worlds beyond Earth that likely harbor subsurface oceans, oceans of liquid water that are salty and perhaps mixed with things like ammonia. These 6 other oceans are trapped beneath the ice shells of worlds like Europa, Enceladus, and along with them, Ganymede, Callisto, 2 other moons of Jupiter. Saturn's moon Titan may have an ocean beneath its icy crust, and possibly even Neptune's curious moon Triton may have an ocean beneath its ice. So there are all these oceans out there, a tremendous volume of liquid water. If you add them all up, it's in excess of 100 times the volume of liquid water found here on Earth. But what sets Europa apart is that we think its ocean has, as a seafloor, rocky silicates. So it might have a seafloor that is comparable to what we see on the bottom of our ocean. There could be hydrothermal vents on the seafloor of Europa. Now, with Ganymede and Callisto and Titan, we think the seafloors of those oceans may well be other phases of ice. So you would potentially have water trapped beneath 2 layers of ice. And having the water-rock interaction is very important, both from the standpoint of the building blocks, having access to the carbon and hydrogen, oxygen, nitrogen, phosphorus, sulfur, and other elements that you need to build life. And with black smokers, hydrothermal vents as an analog, those systems are very good both for providing the chemistry to help power life and possibly also to provide the chemistry that could be important for the origin of life. And so Enceladus and Europa satisfy that rocky seafloor constraint, but then Europa in particular, we think its ocean has been around for a very long time. With Enceladus, we don't really know how long its ocean has been around. It could be an ocean that's 10,000 years old. It could be an ocean that's 1 million years old. It could be an ocean that's billions of years old. We just don't know yet. So Europa really kind of comes to the top in satisfying these constraints of liquid water, building blocks for life, energy, and time.
Very cool, very cool. So Bobak, what really gets you passionate about Europa?
Well, I mean, Kevin's points are all pretty outstanding. For me, I like it in large part because I like the challenge of it. I think, that's one of the reasons why I want to do this sort of work, and I think that Europa and Mars and Titan have sort of been on the kind of and Venus, for me at least, the bucket list of places that I want to visit in the solar system. Not personally, obviously, robotically, is the hope. And it's a challenging environment. It's a difficult problem, and ultimately, I mean, who doesn't want to see underneath the ice for the first time? And I'd like to make that a reality in my lifetime. So these studies and then continuing that hopefully into future generations of missions there are something I want to kind of contribute to and build off of.
All right, well, I'll go ahead and go next. So I can echo what Bobak and Kevin have said, that Europa is one of those really fascinating places in the solar system, both from a chemistry perspective and possibly a biology perspective. So I'm a chemist, and if you just even look at the surface of Europa, it's fascinating. It's got all these cracks and fissures, and it's got this red stuff on the surface. We don't even know what that is. We think that it might be sulfur-based, but we're not sure yet because we need to send a mission to go there and sample it. And then from a biology perspective, this has, like Kevin said, all of the ingredients for life. It's got the water, it has energy, and it has chemistry. It has the potential to have these energy sources of hydrothermal vents. So it's a really fascinating place, and we just want to know more about it.
That's pretty awesome.
Oh, sorry, guys, I missed half that conversation.
We missed you.
I'm back. Over to you, Trace.
You're back. Sorry, guys. Seem to be having some internet issues over at HQ here.
It's all down to the earthquake, Trace.
Yeah, probably.
Where were we?
Are we back? Anybody hear us?
Yeah, it's working. It's working. So now we know that Europa is kind of important. Why hasn't NASA sent a mission to the icy moon yet? That's what I want to know.
Yeah. What's with the delay, guys? Come on, let's go.
Come on, we should be there already, you know?
Yeah, I first started working towards this mission nearly 15 years ago, and so it's kind of depressing that we're not there yet. There are, frankly, I need to be careful what I say about budgetary issues and all that, so I won't comment on the budget. Suffice to say that aside from some radiation challenges, there is nothing technological that gets in the way of us doing this mission. It's not like we need to invent warp drive. Brilliant engineers like Bobak can get this mission done, and so that's part of you know, there's nothing technological or scientific standing in the way. We just need the willpower, which in part is based in the public desire to do this kind of exploration. And so it's exciting to see the public getting more and more interested and realizing the potential of exploring this vast, global, 100-kilometer deep ocean that's been around for billions of years, and getting excited about the potential of finding some bizarre deep ocean squid or something there beneath the ice. So you know, if we can continue to beat the drum and get the public excited about this, I think we can get some of the great exploration done. You know, our motto here at JPL is "Dare Mighty Things," and I think one of the mightiest things we can dare to do is to get out there and explore worlds like Europa.
For sure, that's awesome. I didn't know you guys had a motto. So I'm going to throw this one to Morgan specifically. If you have a background, obviously, studying microbes in pretty extreme environments. So we've talked about Extremophiles on DNews, discoverynews.com. Is like the study of Extremophiles going to help potential detection of life on Europa, say? Absolutely, I think so. So like I said before, every place that we've looked for life on Earth, we found it. This includes places in Antarctica, very deep lakes that have been isolated from the world around them, no sunlight, the only energy source being geothermal. And we find these places are still teeming with life. And we can learn things about the types of organisms we find there, what type of energy sources they use, what minerals they take advantage of. A lot of them will use what are called redox gradients. So they basically will take a chemical reaction, and as that reaction goes from a high energy level to a lower one, they'll use that energy to be able to sustain life. And so we will look for certain characteristics of these organisms that we find in all of these extreme places that may use similar forms of energy or may need to use other sort of protection techniques. For example, to survive in a very cold environment, your cell wall, your cell membrane needs to be composed of slightly different things than normal cells. So we can use these as potential markers to look for. Now again, there's always going to be that argument of whether we're looking for life as we know it or new life. But we have to start with what we know, and there are plenty of organisms on Earth that could be living in Europa's ocean right now in terms of surviving the temperature, the pressure, and even the energy conditions of not being accessible, not having any access to sunlight. So we could transplant those organisms right now and they could survive in that ocean, no problem. So let's start looking for those, and then if we have any other indicators of some other weird forms of life, we can look for those too. But it's nice to start with this background of looking at extremophiles and then going from there.
Hey, and I'm just going to prompt Morgan to comment. She has a really nice paper on a technique that she's developed to look at some of these key molecules, and it's got the cover of the Science Journal. Morgan, you want to just say a little bit about that experiment?
Nice.
Sure. Yeah. So we've recently published a paper. Kevin's a co-author because he helped us collect the samples we analyzed. This is on the cover of Analytical Methods, and we basically looked for one certain molecule that is present in all forms of life that we know. It's called a fatty acid. This is present in the cell membranes, the cell walls of all kingdoms of life. And one nice thing about it is that based on the length of the carbon chain of these fatty acids, they act as biomarkers. Typically, life will add on carbons in units of 2. So if we see, for example, a fatty acid that has a chain length that's 18 carbons long, and then we'll see one that's 20 carbons long, and then we'll see one that's 22. It goes in this sort of 2-carbon spacing. So that can be just like if you look for the chiral handedness of amino acids. It's something that's characteristic of life as we know it. And so we developed a technique that uses a lab-on-a-chip technology, so very, very tiny devices, you know, this big around or even smaller, that takes tiny, tiny samples, smaller than just a single droplet of water, and can detect these fatty acids, these biomarkers, down to the microliter scale, which is, let's see, I think that's parts per billion level. So we're working on improving the sensitivity, but this is the first time anyone is able to look at both short and long chains of these particular biomarkers and basically be able to address the whole range where we think it might be important to look for life. And
so
Kevin, I should say, Kevin was on a submersible that collected samples that we analyzed from a hydrothermal vent. Kevin, do you want to talk a little bit about that trip you took?
No, well, I was just going to mention that it's the type of instrument that Morgan's working on that would be exciting to put on a submersible or melt probe or something like that that goes down into the ice shell or into the water of Europa's ocean, because it could do the chemical measurements that could help us figure out whether or not we've found life on a distant world.
Yeah,
sure.
I suppose in connection with that point about the submersible, because we had a question from one of our viewers, Samuel Gonzalez. How thick is the ice, and what are there future plans to drill it? Because you're working on a prototype, I think, and this could be used to go through the ice. But how thick is the ice? I mean, we're talking like a big barrier here, aren't we?
Sadly, at this point, we only have sort of a global idea of how thick the ice is, and there are debates that ripple through the planetary science community. I happen to think that the ice shell is relatively thin, and by relatively thin, I mean just a few kilometers in thickness, comparable to the Antarctic ice sheet. So Antarctica's ice sheet is about 4 kilometers in thickness. There are others who argue that Europa's ice sheet is maybe 15 kilometers thick. And the reality may be that in some places Europa's ice shell is very thin, in other places it's quite a bit thicker. But one of the goals of an upcoming mission, and maybe Bobak can speak to this about the latest plans, but one of the goals would be to use various instrumentation like ice penetrating radar to characterize at nearly a global scale what the variations are in thickness and potentially find the path of least resistance for a future melt probe that would then get down into that ocean.
Yeah, that's cool. So Bobak, just quickly going to a project you're working on. I mean, what would your ideal mission to Europa look like, and can you speak to any of the cool stuff you're currently planning for Europa?
Sure. Well, I think ideal and practical are kind of two different things. Obviously, the Jupiter environment's pretty harsh on all of our electrical. Well, I don't know if that's obvious to everybody, but there's a very strong radiation environment in Jupiter, and that makes it very hard for us to spend a lot of time near Jupiter. So the practical solution is to find a balance between spending a lot of time right next to Europa in the harsh radiation environment versus getting away from that environment and kind of lifetime versus, I guess, how much data you can acquire immediately. And one of the big challenges there is how much data we can acquire. I think when you think about how far away Jupiter is, it's pretty far away. It's roughly about 5 times on average the distance from Earth to the Sun. So how much data volume we can get back even is a real challenge. So my ideal mission, of course, is something where we can go almost like Viking, where we can go with an orbiter map and then even release a lander. I think in the reality, we're faced with a mission that we have to go and understand Europa first. Certainly, one of the instruments that would be would be very valuable as an ice penetrating radar. I think that's in kind of in the science goals. There's also cameras, for example, for categorizing Europa at different scales, even down to the landed, maybe a future lander kind of scale. And then getting that data back to Earth somehow, which is involves enough time to actually take all this data, which even for us with our cell phones, sometimes downloading a movie or an image or it can take a while. And now imagine that from a different planet. So we need to have time both to take the data and to get it back, and that's one of the big challenges that's facing us.
Yeah, actually, we just got a question from Vasco Ferreira. He's from Portugal, he says, and he's considering the difficulties of working with robots on Mars. How much more difficult will it be to work with a robot on Europa? Because Mars is how many minutes radio? Is it 20 minutes?
Yeah, so Mars at its on a good day is a few minutes each way at the speed of light, and up to about 20 minutes in the worst case each way. So it can be painful. The way we operate the rover is by sending a daily set of commands and watching the rover execute them, and then getting the results back via the orbiters. An orbiter or a mission that doesn't land on Europa has an advantage of being able to most of the time be able to see Earth. And so that's one of the big advantages. But a landed system eventually, or submersible, or anything that we're talking about in the future that I think all of us really want to see happen, there's a lot of logistical challenges, and that involves maybe having a relay system in place, or coming up with clever ways of putting an antenna on the surface so we can do these things. And even that can be challenging because we don't know what the surrounding environment is. There's a lot of high elevation stuff. If you think that there's these cliffs of ice and things around us, and if you look at, I think the artist concept graphic there, you can kind of see a little bit of that. But even then, you might have you might be blocked on a lot of sides by these sort of icy walls, and that might be a challenge. So there are some real technical things, and I think having a mission go there first to sort of categorize and understand it will help us a lot in terms of the next generation of hopefully landed missions. Yeah, you can see a little bit in that graphic. We don't have a good sense, and Kevin can talk a lot more, but we kind of have a little bit. We have a good global map, and then we have a sparse smattering of relatively high-resolution data, but we haven't had a lot of visitors to Europa yet.
Yeah, and this graphic is great to show. And then if we can bring up the Europa bands image, it'd be worth just showing that to the audience, because this captures a lot of the interesting geology of Europa. And so yeah, this image, there's so much going on here, but all of those fractures we think may have some connection to the tidal tug and pull. One of the questions that hasn't come up, but I think maybe people appreciate at this point, is that how can this liquid water exist so far away from the sun? Well, it exists on Europa in part due to that tidal tug and pull that Europa feels as it goes around Jupiter, which is some 318 times as massive as the Earth. And we're all familiar with the tidal tug and pull of the Earth-Moon system. Now imagine your tiny little Europa, which is about the size of our moon, and you're getting swung around by Jupiter. So those cracks that you see in the ice there, we think may be caused by the tidal flexing. And in some cases, and in particular in that broad red band that you see going from left to right in this image, that may very well be a band that's almost akin to a mid-ocean spreading ridge, where you've got material coming up like a conveyor belt from below and then gradually spreading out. And so in the middle, what I would love to see with a future mission is instruments like spectrometers that can characterize the nature of that red material. Is it salt from an ocean below? Does it have organics? A camera that can figure out the geology of what's happening in that dilational band there. And then this radar that could tell us how far down you have to go through the ice before you encounter liquid water. So just looking at an image like this immediately gets the imagination going. And then the thought of putting a lander down to then eventually drill through and take the path of least resistance to the ocean, that's the dream of dreams.
Right. So I guess we have what observations do we have then so far that hint that there's life down there, other than we have images like this, and but what else do we have that kind of gives us an idea? It's not just the fact that there's water there, although that's a big part of it.
Yeah, so I'll just comment briefly on that, and that is that the Galileo spacecraft flew by Europa several times. The Galileo spacecraft was orbiting Jupiter back in the late 1990s and the early part of the 2000s, and the vast majority of our understanding about the existence of Europa's liquid water ocean comes from that mission. We do have Voyager data, a little bit of Cassini data when Cassini flew by Europa, and then we've got ground-based telescope data. And it's quite frustrating because we've got just enough data, just enough observations to literally wet our palate with this ocean, but not enough to figure out whether or not it's habitable. And the key data sets that Galileo returned were first spectroscopy and images showing a surface of water ice, then gravity data or slight perturbations in the trajectory of the Galileo spacecraft as it flew by Europa, and that tells you about the internal mass distribution. And then the last piece of the puzzle is the magnetometer data, the essentially fancy compass data, that detected an induced magnetic field at Europa that is created by the time-varying magnetic field of Jupiter. In other words, Europa does not have its own magnetic field. The magnetic field around Europa is being created by Jupiter, and in order to have this induced magnetic field from a physics standpoint, and this is fundamental physics, this is Maxwell's equations, Faraday, this is beautiful physics. In order to have that induced magnetic field, you need a near-surface conducting layer. And it turns out that water ice is not conductive enough. Silicates, rocks, are not conductive enough. The iron core is certainly conductive, but it's too small and far away. So the Occam's razor, the best explanation for the induced magnetic field signature observed by Galileo, is a salty liquid water layer a few kilometers below the surface of Europa's icy shell.
So in addition to that, I mean, so it's pretty definitive that we know there's a subsurface ocean there. Are there any other elements on the surface of Europa that suggests that could provide nutrients for life, or perhaps life is actually producing it? And what kind of experiments could we send there to actually perhaps even detect life from say, an orbit around Europa?
Well, that's where it gets a little tricky. So
Yeah.
there are a lot of different organic and inorganic species that life can use to take advantage of chemical reactions to survive. Sulfates and sulfites, so sulfur with oxygen bound to it, is an example of those. And we may see some evidence, some of those dark reddish patches on the surface of Europa might be from sulfates, but we're still not sure if those are from the interior of Europa or if they're from Io, which is one of Europa's neighboring moons that's got a lot of volcanoes and is kind of just spewing stuff out into orbit around Jupiter, and so Europa may be accumulating some things from that as well. But life can certainly use those types of organic and inorganic salts as energy sources to survive, whether through reduction or oxidation, so taking or removing electrons, or giving or receiving electrons. That's one way that life can use non-sunlight-based energy to survive. So we've come up with lists of things that we would look for that would indicate whether or not life was there. But the trouble is a lot of these things can be produced abiotically too, so not by life. So one of the things whenever we try to answer this question about life is to look for multiple lines of evidence that can lead to the same conclusion of life, where if you just had one, that might not be convincing enough. But if you have two or three things that all could only be present if life was present statistically, then you've got a much stronger case. So we're working on building that, but it's going to be a challenge, and that's okay. That's what we do. Like Kevin said, we dare mighty things, and we love challenges. That's why we all work here at JPL.
There's one of my favorite lines in the published scientific literature
What do you guys
from
think? Sorry, I keep cutting in and out, so I'm not sure where people are.
no.
Go ahead, Kevin.
Delay trade.
I was just going on this issue of how you actually know that you've found life. There's a great paper from the Galileo mission that goes back to, I believe it's 1992. Carl Sagan was the first author. Bob Carlson here at JPL was the second author, and it was a wonderful thought experiment. And the idea was this: the Galileo spacecraft, in order to get out to Jupiter, it had to go on some gravity assists in the inner solar system, and then it flew by the Earth. And so Carl Sagan and Bob Carlson and others decided to use the instrumentation on the Galileo spacecraft to see whether or not they could find life on Earth. You know, it's a good test case. You know, we've got ground truth that life is actually here, and so using the spectrometer and using the camera, they were able to see a red edge of photosynthesis. They were able to see features of methane and ozone and oxygen and CO2 that indicated chemical disequilibrium that would be produced by life. And so there was sort of a proof positive example of spacecraft instrumentation being able to independently validate that planet Earth was alive. Now, transporting Galileo out to Europa, you have this challenge of, okay, well, there the signs of life might be much more subtle, and compounded with that, you've got the radiation problem where any large organics, like, you know, let's imagine that life on Europa is powered by, or the information molecule is DNA. If you put DNA up on the surface of Europa, it gets bombarded by the radiation and destroyed quite rapidly. But we've actually done this experiment in our lab, and we've irradiated microbes under Europa-like conditions. What we find is you still get some of these polymerized building blocks. You still see some patterns of these molecules of life, comparable to what Morgan was saying. And so we think that if we were to see some of those spectroscopic features, we might be able to build a case for biomolecules on the surface. But in that paper, what Sagan and colleagues say at the end is, at the end of the day, when you take all of this evidence together, we have to be very strict, and life must be the hypothesis of last resort. We have to rule out all other possible hypotheses, because detection of life is such a profound discovery. It needs to be the hypothesis of last resort when we concatenate all the data sets.
I'm sorry, it looks like we've missed Trace, and apparently there's two of me now. Internet got very bad all of a sudden. I'm sorry about this. So I think going to Bobak, I kind of wanted to know what, I mean, of course, you know, landing on Mars is one thing, but landing on Europa would be an entirely different endeavor. It would be an incredibly difficult thing to do, because of course Europa doesn't have an atmosphere, and we had a few questions asking, you know, how is the climate different on Europa that it is on Mars, and of course there is no atmosphere. So how would you account for that? Say if you did actually manage to get a lander mission to actually go down and actually see, perhaps take samples up close, how would you actually deal with that from an engineering perspective?
Well, there's a number of ways, but in many ways it's actually easier, because you know, Mars' atmosphere isn't quite as thick as the Earth's, so it's something that you can't ignore, and yet it's not the best for slowing you down. Like, you know, on the Earth you can really come down mostly all the way down on parachutes. But with Europa we can do, you know, a propelled descent, which is what we've demonstrated on the Moon, I guess, Earth's moon before. So, you know, it would probably be a similar mission to that. We would, you know, kind of get into a injection orbit, do a Jupiter orbit insertion, and then once we got near Europa, we would kind of get into orbit around that, and then do a descend, burn, slow down, and then fire rockets. But I mean, the biggest concern always with Europa, for us at least, and we have the advantage of now years of Mars exploration and multiple missions to go there, is we sort of know a little bit about the habitable environment of Mars. We know how likely it is that anything we could bring from Earth would survive on the surface, which is very unlikely. With Europa, as Kevin and Morgan are kind of saying here, it's actually a really great place in many ways. Maybe not the immediate surface, but it's a great place for life. And so we have to be far more concerned, actually, about the planetary protection aspect, both even in an orbiter or a lander, until we actually understand that environment a little bit better. And I think that will be the really tricky part, is how do you make sure that the data that you get is really the truth from Europa and not something that you brought with you. And you don't want to take something there, even on a first mission, that a subsequent mission finds. So that's the really hard part about a Europa mission too, that we just don't know enough about it still to say, hey, this is how you design for that problem, because the problem is sort of unbounded.
I suppose you touched on this, with the planetary protection. I mean, are there some ethical questions that have been raised about actually sending a mission to Europa? Because it is such a pristine environment. I mean, should we leave it well enough alone, or are the questions just too big for us not to land something on the planet, on the moon? I mean, are the ethical questions that big, do you think?
Well, I mean, Kevin and probably can talk to this more, but we have a decadal survey at NASA where the science community at large talks about what their highest priorities are, and Europa has really been at the top of that list in the last, I think, 2 decadal surveys. I might have gotten that wrong, along with Mars sample return. So I would say that yes, for the science community, this is a pretty big goal. I think that ultimately the burden comes down to the teams developing these instruments and spacecraft to do that, to fall within the regulations and not necessarily ethical science, although that's implied, but making sure that the science we do get is as as clean and devoid of any human error or human-induced error that's possible.
That's cool.
Yeah, and I'll just add that though planetary protection presents a challenge, it's not an insurmountable challenge. It's a matter of baking your spacecraft. It's about essentially being careful, and so we can do both. We can do the exploration and pursue these profound questions while simultaneously making sure that if there are Europans living beneath the ice, we have minimal impact. We try and adopt a leave no trace policy.
Oh, leave no trace. That's it. Taking it.
Yes, the trace is your cue.
So since Europa has liquid on the surface, it's got organic molecules. Does the soup? This is a question from Janine Buckenmeyer, by the way. Does the soup have to be water alone, or can it be some kind of, they talk about the primordial soup of life here. Are we looking for sulfur and nitrogen similar to here, or do we have our eyes more widely set than that, a little wider net for Europa? What do you think, Morgan?
Well, we're pretty sure that the subsurface liquid ocean of Europa most likely has some dissolved salts in it, similar to the salinities of our oceans here on Earth. So probably sodium chloride, maybe some carbonates, sulfates, things like that. But we're not entirely sure what that composition is. These are just guesses, again, until we go there and make the physical measurements. We're not entirely sure. But those salts would add to it being a conducting layer like Kevin talked about, which is why we were able to detect it in the first place. And those similar magnetometer measurements are how we know that a lot of other icy worlds, like Titan, like Callisto, and Ganymede, also have global subsurface, presumably salty water oceans. So the composition of those, the types and amounts of those salts may give us some constraints on the types of life if we do find some that we might expect to find. But again, right now that sample space is pretty big, and we'd like to make it a little smaller before we can start to draw some meaningful conclusions.
Yeah, that makes a lot of sense.
Related to that, the wide net that the questionnaire asked. You can think about a place like Titan. Titan is a beautiful and bizarre world with these liquid methane, ethane lakes on the surface. And I would love to go and send a little sailboat or submersible into those lakes. But at Titan, Titan's a place where we ask the question of, is there weird life going on elsewhere in our solar system? At Titan, the solvent for life would be this liquid methane and ethane. It would not be water, as is the case for life on Earth. And it could well be that life can work with that kind of hydrocarbon solvent. But here's where, from a sort of hypothesis standpoint, we, at JPL and within NASA, when we formulate our questions and prioritize our missions, we have to do both hypothesis-driven science and discovery-driven science. Searching for life on Titan would primarily be discovery-driven science, because as of yet, we don't have a framework for life working under those chemical conditions. Whereas places like Europa and possibly Enceladus, we know that life works with liquid water as the solvent, then a combination of some 54 elements when you look at the periodic table, and some chemical disequilibrium. So when it comes to hypothesis-driven science and exploration, these worlds that at least are comparable to what we know works here on Earth kind of rank a little bit above these discovery-driven worlds.
I have the ultimate question. It's the elephant in the room we're all thinking about. Europan jellyfish. So what are the chances of finding complex organisms on Europa, the ones that are multicellular? We're not talking like bacteria here. How about multicellular creatures that swim around in this ocean? I mean, it was kind of in the movie Europa.
Don't do it. Don't do it.
I haven't seen it yet. Don't ruin that for me.
How can I?
We'll have a viewing party.
Just watch it. It's awesome. So, is it possible? That was a question from Michael Daintith. He wonders if there's the potential for finding complex microorganisms. And I think I read somewhere that it's all about the oxygen content in the oceans. Well, that will depend on what kind of complex life you may get beyond the microbial. What are your views on this? Is this like a mainstream thought, or is this kind of still a little bit out there? And I can go to anybody.
Well, I think instead of jellyfish, I might look for some of the multicellular organisms we see around hydrothermal vents here on Earth. We see crustaceans, so crabs. We see these sort of long tubular-like feeders. So I would look for things more like that, probably down on the seafloor. And Kevin, I'm sure, can tell you a lot about these because he's been in these submersibles and seen these with his own eyes.
Well, I'll start at the surface of Europa, because here's where, again, the situation at Europa is just very beautiful from a physics and a chemistry standpoint. The radiation that drives engineers like Bobak nuts could actually be a critical point for helping power not just microbial life, but also perhaps giving a leg up to the emergence of complex organisms. When you look at the evolution of life on Earth and the Ediacaran and ultimately the Cambrian explosion, part of why we think life evolved into multicellular complex life on Earth is that there was enough oxygen. And this comes back to the redox gradients that Morgan mentioned, where, you know, if you think about microbes, microbes are kind of getting the business of life done by using the chemical equivalent of the tiniest little watch battery, okay? Whereas we humans, these large complex creatures, we're using the chemical equivalent of a car battery. And the biochemical car battery is basically taking oxygen and connecting it with hydrocarbons or carbohydrates, as we do. You know, we breathe in oxygen to help burn the carbohydrates that we eat. So oxygen and energy availability is a critical component, we think, of why complex life emerged on Earth. Out at Europa, that radiation that makes building spacecraft very hard splits apart the water ice on the surface, and it forms things like molecular oxygen and hydrogen peroxide. And we've actually mapped out that hydrogen peroxide and the oxygen on Europa, and we know it's there, trapped in the ice. And so it could be this beautiful situation where the radiation environment produces oxygen, which then, if you've got subduction occurring, could deliver that radiation-produced oxygen to the ocean below, helping to oxygenate the ocean and potentially providing enough chemical energy to allow for the emergence of complex life. Now, whether or not the emergence of complex multicellular life is inevitable, whether it's contingent on something or a convergent property of evolution, that's a whole different story. But that's part of why I want to go to Europa, so we can probe these questions and we can have a sample size. We can have a separate tree of life. Now, for all of the diversity of life on Earth, we're all connected by the same genetic tree of life and the same evolutionary tree. At Europa, maybe it's a whole different tree, and there's a lot to learn from studying a different tree.
That's so cool. Like, just the idea that there's a whole different evolutionary basis for life out there, that alone is exciting. I mean, that, as you said, that alone is a reason to go and try it out. A person I asked online, Music Fluff is their name. How would you deal? Let's say that there is radiation and there are adverse weather conditions and all sorts of other things to deal with. Bobak, how would the radiation, temperature, how would that affect any kind of potential missions?
Well, certainly colder temperatures, not just at the surface, but when we're kind of away from the surface is one of the issues. So we have to use a great deal of our energy to keep certain parts of the spacecraft at the right temperatures. Some things like to be very cold, some things like to be very warm, some things don't want to see the sun, some things like that warmth from the sun. So those are always the balancing issues. Radiation is a big one once you really get beyond the Earth, and we've known that for a long time. With what often happens for us is we evaluate components and hardware and things like that have been qualified for higher radiation. That often means that they are already 5 or 6 years out of date. I mean, Curiosity's computing systems are probably equivalent to a computer around 10 years ago. So it's not necessarily the most up to date. And then we have some tricks up our sleeves. In addition to that, we can encase things in aluminum or other materials to sort of block out some of the radiation. But that being said, there are still sensor heads and things like that always will need to be outside of a blockade. They need to see the interesting thing, and therefore are also going to see some radiation. And so those are the kind of the engineering trades that people have to make in terms of designing these missions. And of course, we can also play with games like at Europa of how much time we spend in the Jovian environment versus getting away from Jupiter a little bit and getting outside of that intense radiation environment. So those are some of the engineering kind of things that we can do. But it's not very likely you'll see your iPhone or the latest computing technology show up on a spacecraft anytime soon.
Yeah, at JPL, the scientists and engineers are always working very closely together because the engineers want to go to the safe places and the scientists want to go to the interesting places, and it's very rare that those two coincide. So we're often tagging back and forth in terms of, okay, well, what place can we go to that sort of meets both of our minimum criteria for being interesting and safe enough that we can actually get there and do the science we want to do.
Morgan, while we've got you here, you talked a little bit before we went on air about all that incredible stuff that's going on behind you. It looks like a chemistry set.
Oh, yeah.
What is it? Where are you right now? Because this is really
so
cool. Because you mentioned that it's a little bit of a bit of Titan going on, a little bit of
yeah. You said it was kind of dangerous.
well, it's not
Cool.
incredibly dangerous. We take all the safety precautions that we should. So we're very, very health conscious here at JPL. We want to make sure our scientists survive to do our experiments. But yeah, so the lab I'm in right now is one of the labs at JPL that is mostly interested in Titan chemistry. So I am very interested in Europa. I'm also very interested in Titan. Just like Kevin said, there are all of these icy moons that fascinate us in different ways. And Titan, like Kevin said, is really bizarre because it's got, instead of liquid water, it's the only other place in the solar system with liquid on its surface, but it's not water. It's liquid hydrocarbons, so methane, ethane, things that are only liquid when it's very cold. And they behave really differently. And so what we do in this laboratory, you can see the fume hood behind me. We've got a Schlenk line, which is just basically a fancy name for this glass tube that has a bunch of little ports on it, and we can look at samples that we don't want exposed to oxygen or exposed to our air. And so what we'll do is we'll make compounds or look at compounds that we think are present on Titan's surface, things like benzene or hydrogen cyanide, which can be pretty dangerous if you don't know how to handle it properly. And then we'll dissolve them in little mini Titan lakes that we make here in the lab. Luckily for us, Titan's surface is only a little bit warmer than liquid nitrogen. Liquid nitrogen temperature is around 78, 79 Kelvin. So we warm it up to Titan surface temperatures, which is around 90, 95 Kelvin. So basically, you can just kind of make like a double boiler, but with liquid nitrogen, and then you can condense methane or ethane or something like that inside, and then dissolve in bunches of stuff, and then we look at what things dissolve, what things don't dissolve, potentially what things could maybe assemble and form more complex structures that might be used by some weird form of life that could be present on Titan. So we're interested in all of these things. And so some of that work we do here in collaboration with a lot of different groups at JPL. It's really interdisciplinary stuff. We've got to talk to geologists to figure out sort of the big picture stuff. We have chemists like myself. We have biologists who are trying to come up with some of these crazy solvents like ethane. So it's a lot of fun. I'm having a really good time.
That's great. It's always fun to have a good time at work.
Yeah, we've actually just published a couple of papers involving benzene and ethane. I can send you guys a few links to that too. It forms this funky, what we call a co-crystal. It's sort of like hydrated minerals on Earth, but instead of the hydrated thing being water, it's liquid ethane, forming inside these cracks and crevices inside benzene's crystal structure. And we're pretty sure that we might find this on Titan one day when we have another lander like the Huygens probe.
That's so cool. So Ian and I both have highlighted two questions, and we only have time for one of them. I think we can combine them, Ian. I think we can do it.
Yeah, we can do it.
I'm going to go with mine, and then you hit with yours right away.
Yeah,
so if we see, you've mentioned Titan, you've mentioned Enceladus, you've mentioned all of these other places. So do you think perhaps we would ever be able to go to those places too? And, Ian?
Oh, you want my question? Yeah, and my
question tied in.
Okay, and this one actually comes from one of our viewers, Vladimir Kim. If you do find life on Europa, what's next? And I just had an addition to that slightly. How would it affect our search for life elsewhere beyond the solar system?
Right.
Wow.
It's a big one. It's a big question, guys.
Well, I think, and Kevin can probably add a lot more to this, if we do find life on Europa or Titan or something like that, if it's similar to life on Earth, I would want to know if it evolved from sort of the same seed, basically. Maybe life was transplanted through what they call panspermia, where it maybe hitched a ride on a meteorite, and that maybe we populated Europa, or maybe we're all Europans originally. I'd want to find out at what point those two kinds of life diverged. That would be really interesting to me, and then just to learn everything humanly possible about it. You know, how is it the same? How is it different? Can we learn from this? Is this more likely to be the kind of life we should look for elsewhere, around, say, in exoplanets and things like that?
Yeah, that's cool. Kevin, what do you think?
Well, I'll just add that the discovery of life elsewhere is not necessarily going to change the way you make your coffee in the morning. You know, you're still probably going to get caught in traffic on your way to work. You know, it's not one of these things that's likely going to revolutionize your day-to-day life, but it does have the potential to revolutionize our understanding of the universe in which we live. Like Morgan was saying, you know, if we go there and can find an independent origin of life, that would represent a second tree. And one of the nice things about Europa is that it's actually a lot harder to contaminate Europa or to do that cross pollination or seeding. Earth and Mars, you know, if we discovered DNA-based life on Mars, that would be kind of suspect. We might think that life arose on Mars and it was transported to the Earth or vice versa. If we go to Europa and discover DNA-based life there, I think that would be a highly compelling case for a second independent origin of DNA-based life. And what that then means is that the origin of life itself could be easy. I mean, at the root of it, that is what Europa has the potential to answer for us. Does life arise wherever the conditions are right? Is the origin of life easy or hard? If we find life within Europa's ocean, then we would want to fully understand that life. But that also opens up the universe to being this biological universe. If there is life on Europa, we can then have some confidence that life arises wherever the conditions are right, be it ocean worlds, icy moons in our solar system, or exoplanets orbiting distant stars. We transform our universe from one that's been a physics, chemistry, and geological universe to one that is now, some 400 years after Galileo, a biological universe.
Wow, that's big. I mean, I think that's probably the best way we can end it there. So, yeah. I want to hope for a biological universe, but maybe that's just me and some of you guys. Thanks a lot for joining us, you guys. That was a whole hour. That was a whole hour of fun. We loved every minute of it. So, guys, if people have other questions, can they come and find you elsewhere? Where can they come? On Twitter? Or do you prefer? Let us know. Kevin?
I'm at Alien Oceans, but despite that I work at one of the most technologically advanced institutions on the planet, I am still a bit of a neophyte on Twitter, so don't expect too much in terms of activity.
Okay, well, if they tweet at you, just make sure you also tweet at NASA JPL. And Bobak, you're a Twitter master. I know that. You're out loud, right?
Yes.
Yeah, so... Morgan, are you not on the Twitters?
Not yet. I've kind of been busy. I'm in the lab. See, I'm in the lab now.
Oh, no, yeah. She's busy, guys.
Yeah, but
she's busy.
I'm on Facebook. I'm on Google Plus a lot, so, you know, I'm happy to answer questions anytime.
Cool. And I'm at Trace Dominguez, in case anybody cares. But go find NASA JPL on Twitter, too. Remember NASA JPL. You can also find at DNews. If you're looking for science every day of the week, subscribe to DNews on YouTube. You can also find NASA JPL out there, and Google+, Facebook, as Morgan said, and Twitter. So if you have any suggestions for what to talk about next month, make sure you send them our way. And we'll see you next time, everybody. Thanks again, everybody. This was great.
Thank you, guys.
Bobak,
Thank you.
What do you got going on? What's that?
Oh, Bobak. Oh, this one's real.
Bye, guys. Thanks.